Namaste and hello everyone. Welcome to the Civil Academy. So, in this series, we have already seen about the evolution of cement, the grades of cement, the properties of cement, the composition of cement, and the Bogue's compound. In today's class, we will learn about the hydration of cement, the importance of hydration of cement, the cement hydration mechanism, the various stages of hydration, and the water requirement for hydration. In the previous class, we have seen regarding the oxide composition of cement with their respective percentages. Now, from that, we can say that if the amount of Na2O present is more than 1%, the cement is called as high alkali cement. And if it is less than 0.3%, it is called as low alkali cement, whereas these numbers are just an arbitrary number which are decided by the engineers. In this process, the active ingredients, that is C2S, C3S, C3A, C4AF, reacts with water. It liberates a considerable amount of heat which is called as heat of liberation or heat of hydration. This is an exothermic reaction over here. The chemical composition of cement typically affects the heat of hydration. Now, this heat of hydration can be measured with a calorimeter as shown over here. Then, the result is plotted as a curve of temperature versus time. Joules per gram or calories per gram are the unit used to measure the heat of hydration. Now, let's learn about the importance of heat of hydration of cement to the civil engineers. We have already discussed this earlier many times that cement is the binding, or you can say the bonding material which is used in concrete. Apart from this, this is the only reactive component present in the concrete. So, unhydrated cement or anhydrous cement does not participate in the binding process. It's only after hydration does cement acquire its adhesive properties. The concrete strength and durability are significantly impacted by the temperature and rate of hydration. Therefore, this rate of hydration of cement is of prime importance. For example, this is a picture of road construction going on. So, the construction has to be carried out and also open for the traffic as soon as possible. Here, we will want a cement which will stiffen rapidly and gain early strength. For this, we have we have to see that the chemical composition should be such that hydration products are formed early. So, in order to achieve that, we must make an effort to ensure that the complexes that are reacted or that reacts more quickly than the others are present in definite amount. Similarly, imagine that the site of construction is very far away from the batching plant. As you can see over here is a batching plant and this is a site of construction. So, in this case, if the initial setting of cement is not increased, then it might so happen that when we reach the construction site, the cement becomes stiff. Here, we have to control the compounds which hydrates very early and stiffens the cement. Then only we can increase the initial setting time of the cement. So, if we alter this Bogue's compound, which we have seen in the previous slide, according to our needs, we can get a variety of cement like RHC or rapid hardening cement. The quantity of C3A is very high over here, and LSC, the low heat cement, the quantity of C3A is very less over here, and so on. Now, let's learn about the cement hydration mechanism. Basically, there are two theories to explain this. The first one is called as the topochemical reaction. The picture over here represents the topochemical reaction. Now, according to the solid state mechanism theory, cement compounds exist in a solid state rather than in a solution state. Now, these compounds are attacked by water in their solid state and are turned into hydrated product. The hydration basically starts at the surface of the compound and reaches to the interior over time. You can see over here, this is cement particles. So, it basically starts at the surface of the particle and then finally reaches to the core of the particle. The second mechanism is the true solution mechanism of cement hydration. Here, when we add water, the cement components dissolve and produces ionic constituents. You can see this represents the true solution reaction. The solutions become supersaturated as a result of the formation of hydrate in the solution. Now, this slow solubility of the hydrates causes the product of cement hydration to precipitate from the supersaturated solution. Now, during hydration, by this true solution mechanism, the original contents are completely reorganized. Now, both this above mechanism occurs in the hydration of cement. Now, in early phases of hydration, where there is enough of water available, true mechanism can be assumed to be occurring, whereas the solid state mechanism continues in the later phase when the mobility of ions is restricted. The rate of hydration is different for all the cement compounds which you have already seen, that is C2S, C3S, C3A and C4AF. The aluminate hydrates at a rate that is significantly very higher to that of silicates. Now, we can say that stiffening of cement paste is due to the hydration of these aluminates, and the hardening is due to the hydration of these silicates. Now, when we add water to the cement, the C3S reacts very rapidly and release calcium ions. Calcium ions, the hydroxide ions, and amount of heat. Now, after it begins, the initial hydrolysis slows down quickly, reducing the amount of heat evolved. The process gradually continues to produce calcium and hydroxide ion until the system is saturated. The calcium hydroxide then begins to crystallize as a result of this. Now, if we see the order of heat of hydration, we can say the C3A is greater than C3S, which is greater than C4AF, is greater than C2S. Similarly, if we talk about the order of rate of hydration, C4AF will be greater than C3A, which will be greater than C3S, which is greater than C2S. Similarly, if we talk about the setting time, we can see then that the C3A is greater than C4AF, which is greater than C3S, and which is greater than C2S. So, similarly, the order of strength also varies. So, this is a schematic representation. Here, which shows us the information of pores of calcium silicate hydrate. This diagram A over here represents that the hydration has not yet begun and the pores are filled with water. As you can see over here. Then the beginning of hydration. Takes place. Then the hydration continues, but there are a lot of empty spaces which are filled with water and calcium hydroxide. See, all the notations are being marked over here. This is hydroxide, the calcium, the water are marked over here. You can refer to the diagram for that. Then the cement starts hardening as most of the parts are filled with CSH, and which is not filled is the calcium hydroxide solution. Now, the process of hydration continues for a longer period of time until water and unhydrated compounds are present in the cement phase. So, if we can go here, the first one says the dissolution phase, then the second one is the nucleation phase, then the growth phase, then after this setting, we can transport it wherever it is required, and then the growth phase, which takes a longer duration of time. So, these are the various stages of hydration of cement. Let's discuss all the stages in details. The stage 1 represents the initial mixing. Where the temperature will be at its peak, as you can see also in this graph, after addition of water to the cement. Now, this heat evolved in this stage is a rapid one and it ceases after 15 minutes. So, the surface releases calcium and hydroxide ions, and when specific quantities are reached, the evolution of calcium hydroxide and calcium silicate hydrate starts. Stage 2 refers to the induction or the dormant period. Now, as a result of stage 1, the hydration products begins to build up around the hydrated cement's nucleus, and this we have already discussed in the previous slides. Now, this stage lasts for a period of 2 to 4 hours, and during this, the hydration is in a standby mode. Here, the concrete remains in, you can say, plastic state for several hours and then starts moving to the solid state. Now, this stage ends with the initial setting. You can write here, it is, you can see it as mentioned over here, the initial setting of the concrete. Now, as soon as the dormant stage completes, the setting process begins and the cement begins to react with the water more quickly. Now, this results in the formation of a new hydration product, and all this occurs in the third stage, that is the hydration acceleration, or you can say the hardening stage. And that is why we call it as to be hydration acceleration, where the heat evolution reaches to this maximum value. Now, after 4 to 8 hours, the final setting has been passed and early hardening just begun. So, the two compounds, that is the C2S and C3S, reacts to form the CSH, that is the calcium silicate hydrate. Now, while using large volume of concrete, it is essential to keep an eye in internal temperature fluctuations, because the concrete's temperature will quickly increase at this point, reaching internal temperatures of about 70 to 80 degrees centigrade or even higher. Now, it is often recommended that this temperature should be kept below 70 degrees centigrade. Then, the stage 4 represents the deceleration period. Now, during this period, you can see over here, during this period, the hydration products are formed, but the reaction and dissolution rates are very slow and controlled. At this stage, temperature reaches its highest point, as you can see over here also. Stage 5 represents the steady state. Now, this is the final stage of hydration product of process of cement. Here, the process of hydrating the remaining water and cement particles has slowed down and is still occurring gradually. Now, here, the formwork used in construction is often removed at this point, and after some time, the concrete will have finished the process of cement hydration and will have reached its full strength. Now, this stage lasts for a longer period of time, obviously, that is equal to the age of the structure. The hydration reaction progresses quite slowly throughout this time. Now, if we summarize all the reactions, the following products are formed as mentioned over here. The C3S and C2S, they react with water and forms CSH, that is the calcium silicate hydrate. You can see the picture also over here. Now, this is a gel-like structure, and also a lot of calcium hydroxide is formed. Here, I would like to mention that CHS gel, also known as tobermorite gel. Now, these crystals are actually very small and fibrous. You can see the picture, and it varies from 2 mm to 10 mm. Now, this is what is responsible for the strength gain in the cement. Now, a fully hydrated Portland cement paste, it contains a CSS phase that accounts for about 50 to 60% of the solid content. The C3A and C4AF that reacts with water to form monosulfates and ettringites. See this here, this is called as gypsum. Now, this gypsum is provided to regulate the reaction, as we know that C3A is the first compound which reacts and it reacts very quickly with water. This is called as the ettringite. Here also you can find the picture of ettringite. Now, when this ettringite reacts with again C3A, it forms monosulfates. Now, the first table gives us the heat of hydration in terms of calories per gram of all the major components present in the cement, that is C3S, C2S, C3A and C4A. As we can see here, the heat of hydration is different for different compounds. That is, for 3 days you can see this C3S is 58, for 90 days 104 and for 13 years you can say it is 122. Similarly, for C2S it will be 12, 42 and 59. For C3A it is 212. As you can see, this is the highest, as I have already said that this is the first compound to react and evolve the highest heat of hydration as soon as it reacts with water. Then 311 you can see over here, then 324. Similarly, for C4AF it is 69, it is 98 and 102. This table over here shows us the reactivity of C3A in clinker and the sulfates in the solution. You can see over here, like if we have both as low, we get normal setting. The one is high and the other is low, we get a quick setting. Similarly, if both are high, we get rapid setting. If one is high and obviously the other one is very low or none, then we call it as a flash setting. And if again low and high, we call it as false setting. So, the factors affecting the hydration of cement are as follows. The first one we can say is the composition of cement. Now, the presence of pure compounds with proper composition is obviously very important. Now, we have already discussed this in today's class, that is with example of road and batching plant also we have seen. The second one is the amount of gypsum. As we know that C3A is the fastest to react with water and leads to the condition of flash set. And we do not get any time for transportation and placing of concrete. So, to overcome this situation, we add gypsum. So that the solubility of C3A is reduced. Next is the fineness of cement. So, fineness basically tells us about the particle size of cement, that is the extent into which the cement is being ground in the manufacturing process. So, as the fineness increases, the rate of hydration also increases. Very important. The last one is the presence of chemical admixture. Now, there are many chemical admixtures available in the market that acts as a retarder and slow down the hydration reaction at very early stage. Moving on, the water required for hydration process. So the minimum amount of water required for complete hydration is about 38%. Now out of this 23% by weight of cement is called as the bound water, and this 15%, 15, is called as the gel water. Now only this 23%, that is called as the bound water, participates in the hydration reaction. This rest 15% is called as gel water, and as because it fills the gel pores. So excess addition of water is undesirable and it is not necessary at all. So there is an interesting quote over here which says the pebbles of knowledge must be bonded together by the cement of experience. On that note, that's all for today. Thank you everyone and keep learning.